My name is Milen Pérez. I am right now working for CARTIF, Fundación CARTIF. It's the technology center located in Spain. This is my presentation about the PCM, is a technology to storage energy. That's all for now. The work its topic, the model and simulation of a thermal storage system based on phase change materials and integrate in a tertiary building. In line with the decarbonization objective of the European Union and the need of energy storage, thermal energy storage systems support the power-to-heat strategy, harness the potential of energy flexibility, and provides an interesting alternative to enhance renewable energy integration in buildings. In this sense, the phase change materials are one of the most promising technologies for building application. Utilize latent energy to offer high energy store density. Their combination with heat pumps enables the implementation of the power-to-heat strategy. In this sense, the general objective is to model and analyze different solutions for the integration of the thermal energy storage system based on PCM. I mean to propose a design that meets the need of CARTIF III building during the summer period and enable improved energy efficiency and flexibility in energy utilization. CARTIF Foundation is a technology center located in Spain. One of the buildings in it is CARTIF III. That is a nearly zero energy building. To meet his electrical demand, have a rooftop solar photovoltaic panel system. About the energy generation and distribution system at CARTIF III, to meet the thermal demand, it has a geothermal and biomass system. On hand, the geothermal system is composed for a ground complex, heat exchange, and a heat pump. And this system supplies the radiant floor and the air handling unit. The radiant floor for heating and for cooling, and the air handling unit only for cooling. This system supplies the office's space. On the other hand, the biomass system supplies the domestic hot water and the air handling unit. This only for heating. And supply the industrial areas and the offices too. The last system is a free cooling system with the OSRI. This only for cooling. Now, what utility can the PCM storage provide? The photovoltaic production is high during the summer season. This starts 8 or 9 every day. And the cooling demand starts early at 6 a.m. every day. That causes the heat pump consume energy from the electrical grid every morning. With the incorporating of the PCM, it is expected to store the excess photovoltaic energy, eliminate the heat pump's electrical consumption in the morning by replacing it with the energy stored in the PCM. In this case, a 9.50 cubic meter tank, PCM tank, will be installed in CARTIF III. In the figure, we can see the discharge and charge mode market of the real tank. Transit simulation model was doing for Google SketchUp, the Trans building and the Transit 17. And the Transit environmental I show in the figure. And we can see 5 modules. These are the building module, the photovoltaic module, the geothermal module, the distribution module, and the PCM module. The analysis of possible integration strategy was based on the definition of 6 case studies in which the operating condition of the PCM in the combination with the existing energy system at the target building are varied. These cases are called the best case, incorporating PCM, simultaneous feeding, and not photovoltaic. Global excess, the last is the minimum power. The first case is the base case scenarios. It represents the current system existing in CARTIF III without the PCM tank, and that means with the electrical guild consumption of the heat pump. The incorporating PCM scenario is compared to the PCM stored to the existing system modeled in the base case, and it set the charging and discharging condition of the PCM. The fundamental conditions for this case are to activate the PCM charging, the photovoltaic energy generated must be greater than the energy consumed by the heat pump. The second condition are, here it is not thermal demand for the building's cooling system and the storage tank. That means the PCM charging cannot occur simultaneously with the other thermal energy demanding system that are the storage tank and the building cooling system. And this occur, the charge PCM occur in this space of time. And to activate the PCM discharge mode, the photovoltaic energy is less than the consumption by the building's cooling system. And when there is thermal demand for building condition and the free cooling system is deactivated. This occurs in this space of time. The simultaneous feeding scenario is changed compared to the previous case as it enables the PCM charging during the period when the building's cooling system is demanding energy. For this, the second condition to activate the PCM charging chain for the PCM will be charged when the heat pump's nominal thermal condition is greater than that consumed by the other thermal energy demanding system. And the next scenarios continue to vary the charging and the discharging condition of the PCM, taking the most efficient scenario from the previous one. The not photovoltaic scenario, this case analyzed the effect of charging the PCM discharge condition, establishing the activation of the discharge mode only when there is not photovoltaic production. This means in this space, the global excess scenario, in this case, it changed the charging and discharging condition of the PCM. The objective is to study how the activity in the building influence the charge and discharge condition of the PCM. To activate the PCM charging, the general photovoltaic energy must be greater than the total energy consumed by the entire building, and that includes light, pumps, machines, and others. And to activate the PCM discharge mode, it's also modified to announce the PCM discharge when the opposite condition of the meet. That means the PCM output lower than the global building's electrical use. The last case are the minimum power scenario. In this case, the charging condition of the PCM is changed. The PCM charge mode is activated when the photovoltaic output is greater than the equivalent heat pump electrical input. For this, the equation describes the minimum energy that the photovoltaic system must generate to activate the PCM. This equation is the Minimum power is the difference between the heat pump thermal output power and thermal input power to the cooling system, affected by the energy efficient ratio of the heat pump. Assessment indicator used to guide the selection of the base case. These are divided into 4 groups: energy, environmental, economic, and operation. The most significant indicator is the number 3, ratio between renewable and non-renewable heat pumps energy use. A comparison between monitoring and simulating results for the best case are made to define if the simulation case is valid. We can see the results are so similar. For this reason, the case is considered valid. The tapes show the result of the edge case study based on the assessment indicator. We can see the simultaneous feed and the minimum power scenario costs show the most significant improvement compared to the best case. On this figure, we can see the result of the simulation for the photovoltaic electrical power, the heat pump electrical power, and the thermal power of the cooling system for the best case and the incorporating PCM scenario. We can see how on the best case, the cooling system meet the high point of thermal demand in the morning. We can see how the heat pump consumes energy from the electrical gear. Then, in the incorporating PCM scenario, the PCM supply the high demand point and the heat pump does not consume energy from the electrical gear. This occurred the most daily with the exception of one day. This study presents the simulation-based evaluating of different operating strategies defined for the integration of the existing PCM bus stage tank into the tertiary building. A complete simulation model of the building and it's a complex energy flexibility has been obtained with accurate no result to the purpose of evaluating PCM integration strategy. The inclusion of the PCM system improves the use of photovoltaic energy in all the proposed scenarios. Best result for the assessment indication apps are obtained for the simple control strategy alone, simultaneous feeding of the PCM and the existing water tank. And the simultaneous feed has reported 95.8% solar energy fraction, will leading to a reduction of cost and emission of 89%. That's all. Thank you very much for your attention. I don't know.